Testing, testing. Testing, testing. Testing, testing. Testing, testing. Okay, I think we're ready to go, maybe? If you can hear me, please type ABC into the chat bar. Yay. Okay. All right, so let's go ahead and get started. Remember, you can type questions into the chat bar if you have any, and don't feel like you're interrupting. It might take me a minute to respond because there is a bit of a lag between when I speak and when you hear me. So, but let's go ahead and get started. Our main topic for today is exponential functions. This is the last topic that's going to be on the upcoming test, test 3, and we'll look at a couple of questions from the test review about this topic as part of the chat as well. But first, let's get it introduced. So we're talking about an exponential function. In mathematics, an exponential function is one which looks like f of x equals b to the x. The key characteristic of an exponential function is that the base of the expression, like the b here, would be a number. Okay, so I don't know, maybe that might be the number 5, for example. Whereas the exponent is going to stay a variable x. Okay, now it might not be that the exponent is just an x. It could be an expression like 3x or 6x or x plus 1, but it's going to vary. So let's look down here at some examples. We're going to identify which of these are exponential functions. And so let's look at part A here. So for A, we have capital F of x equals x squared. So in this case, the base of this function is a variable x, and the exponent is a number 2. So does that fit the description of an exponential function? So remember, in an exponential function, the base is a number and the variable is an exponent. So actually, no, this is not an exponential function. Actually, this is a type of function we've seen before, right? This is y equals x squared, which is our basic quadratic function, the square function, which, by the way, when you graph it, is a parabola, which is not what exponential functions look like. We'll talk about what those look like in a minute. But a is definitely not an exponential function. All right, so let's look at part B. For part B, the base is the number 2, and the exponent is the variable x. So yes, this part B is an exponential function. Okay, in part C, we have capital H of x equals the base 1/2 to the power of 5x. What do you think? Is that an exponential function? So type into the chat bar yes or no. All right, good, Jaylene. Yes is the correct answer. The base is the number 1/2. And the exponent is 5x, which is a variable. It's a variable expression. It's not just an x, but that's okay. So this actually is an exponential function, yes. Okay. The only base, so we have a base of 1/2, so that might throw you off, but actually the only base that's not allowed is 1. And the reason is because if you raise 1 to any power, you just get 1. So if we were to write y equals 1 to the x, that would be the same as just y equals 1, which is a constant. It's not an exponential function. But any other base, well, I take that back. 0 also. You can't have 0. And we only use positive numbers when we're doing our base b. So we're going to think of b as being any number greater than 0 except for 1. Okay, so 1/2 works. All right, now let's look at part D. So for part D, you can see that there's an exponential expression here, 3 to the x. It is being multiplied by 5, and then 1 is being added to it. That's okay. So this is considered an exponential function. We have a base of 3, and the exponent is x. And then what's happening is we're just performing transformations on this function. So it's still an exponential function, but we're just adjusting it a little bit. So this is actually, yes, considered an exponential function. All right, so let me show you some graphs of B, C, and D so you can get an idea what the graphs of exponential functions look like. So the function g, ignore this, the function g of x equals 2 to the x is the graph in blue here. Ignore the red line, please. So just to give you a couple of examples of points that will be on our function g, let's plug in, say, -1, 0, and 1. So what would 2 to the negative first power be equal to? Well, remember, a negative exponent indicates that you're going to take the reciprocal. So this is going to be 1/2, or 1/2. And then if we plug 0 in, anything to the 0 power is 1. So by the way, as a result, whenever you have an exponential function of this form, you're going to always go through the point 0, 1. And then 2 to the first is just 2. So we have -1, 1/2, 0, 1, and 1, 2. So these are going to be about here. Let's see, nope. Here. I think the scale here is by 2s, 2, 4, 6, 8, 10. So at 1, 2, 0, 1, and -1, 1/2 would be here on the graph. So that's 1, 2, 0, 1, and -1, 1/2. Okay? And what you'll notice is if we keep plugging in larger and larger values for x, like for example, I don't know, the number 4, then we would get 2 to the 4th, which is actually 16. You can see that it goes way up here. So 4, 16. Going to be way up here. So the function gets very large very quickly on the positive side. Now when you plug in negatives, it causes you to get tiny little fractions. but it never causes you to get 0. You can't raise 2 to a power and get 0. So another thing that we need to be aware of is that there is actually an asymptote. It looks like it's touching the axis, but it's not. It's getting very, very close to it, but it never crosses the line y equals 0. Y equals 0 is an asymptote. Okay, so that's what 2 to the x looks like. If you recall, h of x was 1/2 to the 5x. This is interesting. H of x equals 1/2 to the 5x. Okay, so this is actually turned the opposite direction, because when you plug in negatives and flip over the 1/2, you get a whole number, so it's larger. When you plug in positives, it stays tiny, a small, small fraction. It still has an asymptote, though, at y equals 0. And then for f of x, remember f of x was 5 times 3 to the x plus 1. So f of x equals 5 times 3 to the x plus 1. We have the same type of graph as 2 to the x when we graph 3 to the x, but this has been transformed. It's been shifted up 1 unit, and it's been stretched vertically as well. So it actually has an asymptote at y equals 1 because it was shifted up 1 unit. And then it looks kind of stretched even taller or skinnier than the 3 to the x would have originally been. All right, so those are just some examples of graphs. I'm going to tell you the general characteristics, and we'll practice in more detail in a minute. But you can see they all have a shape that looks either like this or like this, and they have a horizontal asymptote. Okay, we're going to add this function to our library of functions, which we saw x squared, x cubed, cube root, square root, all the functions you need to know. We're going to add to that right now. Remember, you can ask questions in the comment section. Okay, so we're going to go to the next page now in our OneNote notebook and talk about the graphing in more detail. Let me fix this real quick. Oops. My OneNote's not happy with me right now. Hold on a second. Okay. All right, so let's talk about the basic graph of the exponential function. And just like when I taught you the graph of x squared, for example, we're going to memorize certain key points. But in this case, it's going to have a b in it instead of having the library function say something like f of x equals 2 to the x. We have to put a b because this same shape will work for any exponential function as long as b is a number bigger than 1. So 2, 3, 4, or even like 3.5, it doesn't matter. Anything bigger than 1, it's going to go through these same general key points. So what I'm going to do is first put a scale on here. So let's say that the scale is like this. 1, 2, 3, -1, negative, whoop. Why my undo button doesn't want to work like it normally does. Okay. All right, so here we go. -1, -2, -3. And then we'll have 1, 2, 3. Okay, so let's say we wanted to plug 0 into this function. We would get b to the 0, which is 1. So your general basic exponential function goes through the point 0, 1. So I'm going to plot 0, 1 here. All right, and then what if I plug in the number 1? Well, then you get b to the first power, which would be just b. So we get a point 1b. Now, I don't know the value of b. I just know that b is above 1. So I'm going to plot b, say, here. This is, let's pretend, the point 1b. It might be lower, it might be higher, but it's above the point 0, 1 for sure. And if I plugged in -1, I would get b to the -1, or 1 over b. And since b is a number bigger than 1, then that's a tiny fraction, right? So at -1, you're down here somewhere between 0 and 1. It's a fraction. Okay, so -1 comma 1 over b. So you could consider these your 3 key points. So if b happens to be 2, your key points would be 1, 2, 0, 1, and -1, 1/2. If b happens to be 3, your points would be 1, 3, 0, 1, and -1, 1/3. And then the other thing you need to always remember is the asymptote. You cannot raise a positive number b to a power and get 0, so it does not ever cross the x-axis, and it never is negative. All right, so if this is our basic graph, could anyone tell me what the domain and range would be? Let's start with the domain. Can you type the domain into the chat bar? Remember, domain is x values. So which x values do we hit? Okay, well, we hit 0, 1, and -1. That's true. But didn't we also have points in between that we just haven't labeled? In fact, this graph goes forever to the left, and even though it's very gradual, if I were to continue graphing, it would continue forever to the right as well. Remember, domain, you want to go furthest point to the left to the furthest point to the right, but there is none. This one continues without bound on the left and the right. So what that means is that the domain is -infinity to infinity. How about the range, though? There are definitely values that we're not including in the range, so it's not going to be -infinity to infinity. What would be the lowest bound on the y values? The bottom of the graph. A value which we do not go beyond. Good, Jaylene, it is 0. So 0 is not actually in our range because there's a horizontal asymptote there we don't cross. So we're going to put a parenthesis, but it is the boundary, the lower boundary of the numbers that we'll include. So 0.1, for example, that would be in our range. We can't come up with a lowest number except for the boundary value 0. If we were including 0, of course, we would put a square bracket, but we're not. We're saying it's everything up until 0. And then the highest value would be infinity, right? It goes on forever. There is no highest value. All right. Now, the graph is going to look a bit different if we have a function where b is a number between 0 and 1. So let's talk about that. So you're still going to get the same 3 values. F of 0 equals b to the 0 is still going to be 1, even if b is a tiny fraction. F of 1 is still going to be b. It's just that b is a small number. And f of -1 is still going to be 1 over b. That's supposed to be a -1. So b to the negative 1 is still 1 over b, but of course, if your number is smaller than 1, like 1/2, when you flip it over, you get a larger number than 1. So b is less than 1, 1 over b is greater than 1. So we have to keep that in mind when we're graphing here. So 0, 1, let's say, is right here. 1b is going to be somewhere down below that because b is a number between 0 and 1, so the y value is small. And then negative 1 over b is going to be a number greater than 1, maybe up here somewhere. So what happens is you get the reverse of the shape that we just saw a minute ago. It's flipped around. It's flipped over the y-axis. And then y equals 0 is still an asymptote. And the domain and range are the same. We still have a domain that goes forever to the left and to the right. We still have a range that cannot go beyond 0, so we start at 0 and go up forever. All right, so these are the two basic graphs that you must memorize for f of x equals any number b to the x power, where b is greater than 0, not equal to 1. So we have two cases, the b values greater than 1 and the b values that are not greater than 1, that are fractions. If it is greater than 1, we have an increasing function. That means it's going up as we read the graph from left to right. If we have a b value that is a fraction, we get a decreasing function. That means that the y values are going down as we read the graph from left to right. So add these to your library of functions. And now let's practice graphing. So we're going to first graph f of x equals 3 to the x, which is your basic exponential function. And then we're going to graph g of x equals 2 to the x minus 1, which requires a transformation. So you still need to remember how to do your transformations. All right, but starting with 3 to the x, we're just going to plot those three key points. F of 0, which is 3 to the 0 or 1, f of 1, which is 3 to the 1 or 3, and f of negative 1, which is 3 to the negative 1 or 1/3. All right, when you plot those points, it will remind you of the shape of the graph. You'll see how it's increasing from left to right. So I'm going to mark off my graph with thirds so I can mark off my fraction there. Okay, so negative 1 1/3 is going to be way down here. 0 1 is going to be right here. And then 1/3 is going to be right here. And now we're going to put in our asymptote before we actually draw the graph, as that way we will remember that the graph does not cross the y-axis. And then we're going to start at the asymptote and very gradually go up, and then it's going to get much, much steeper very quickly. It's the fact that this exponential function gets very steep very fast in the positive side of the graph that we refer to often as exponential growth, right? So every time we increase x by 1, it triples the value of the y. So it starts to get very big very quickly, and we refer to that as exponential growth, and it has a lot of applications in science, and as we'll see also in banking, earning interest, compound interest. But before we get to all that, now let's graph g of x equals 2 to the x minus 1. All right, so normally your 3 key points would be, you would plug in 0 and 1 and -1. And if we were just gonna, let's go ahead and graph 2 to the x first. So actually I'm gonna, since I'm not using function notation here, if I were to graph 2 to the x, what would I get if I plug in x equals 0, x equals 1, and x equals -1? So 2 to the 0 is just 1. 2 to the first would be 2, and 2 to the -1 would be 1/2. So we have the point 0, 1, 1, 2, and -1, 1/2 is what I would normally be graphing. And then I would have my asymptote at y equals 0. So these would be the key points of the parent function, right, without the -1. Now, what is the -1 going to affect on the graph? Is it on the inside of the function or the outside of the function? So to be on the inside of the function, it has to affect the x or be inside the exponent, which this is not. So this is on the outside of the function, as we discussed when we were talking about transformations. And so it affects the y value, right? It's going to subtract 1 from each y value. So if the key points on the parent function 2 to the x are these, then all we need to do is to subtract 1 from each y value, and we can figure out where the new function will be located in the coordinate system. All right, so subtracting 1 from 1, that gives us 0, 0. Subtracting 1 from 2, we get 1, 1. Subtracting 1 from 1/2, we're going to get -1/2. And subtracting 1 from y equals 0, we get y equals -1. So you can see the asymptote was affected by a vertical shift downward. All right, we're going to plot then -1. So let me mark off a scale here. Okay, so our asymptote is at y equals -1. All right, this graph goes through the points. Let's go scroll back up here a little bit. 0, 0, 1, 1, and -1, -1/2. Should be about there. Okay, now once you plot those 3 key points, you can see which way it's going to grow. So the left side is going to just gradually grow along the asymptote. Then we're going to go through these 3 points, and then it's going to start growing really, really fast. So this would be the graph of 2 to the x minus 1. It looks just like the graph of 2 to the x, but shifted down 1 unit. Okay. The next thing we're going to do is look at a couple of exercises from the test review. Remember, your test review is posted in your OneNote notebook. Here's the test reviews folder, and we have one for test 1 and test 2 and test 3 here. Okay, this is the same test review from your My Math Lab. It's just that I've printed out one version of it in case you need it. All right, so let's take a look here. So one of the things that we want to make sure that you can do, so work on this at home with your calculator. Make sure that you can raise any number to any power. So for example, in this case, they're asking you to raise 3 to the power of -3.5. So in your calculator, if you're using the TI-30X2S, remember the power symbol looks like this. In other calculators, instead of being a caret symbol or an upward arrow, it looks like y to the x or x to the y or a to the b. But you need to be able to calculate something like this. So test yourself, make sure that on your calculator you can get 0.021. The other thing I want to call to your attention is expressions like this one that have the base, which is the number e. So e is an irrational number. That is a useful one that occurs naturally in a lot of applications. So we use it a lot. E is about 2.7-ish. So in your calculator, you're going to have to find the E button, just like you can find the pi button. It often is on the same key that you'll see natural log, which is ln. So you might have to use the second button or shift button to get to it, but you're going to look for an e to the x button. Okay, and so you'll hit that button, and then the calculator will ask you for the exponent, and you'll put in 1.9. So make sure that you get about 6.686 when you plug that into your calculator. All right, but now we're going to go back to talking about graphs. So let me make this a little bit bigger here. All right, so this is a sample problem which is multiple choice. It says the graph of an exponential function is given. Select the function for the graph from the list. Okay, so notice that this is a decreasing function, which we would normally think we would have a base between 0 and 1, like 1/5, for example. But 1/5 is not an option for the base here. So what that means is, or 1/3 or 1/4 or any fraction less than 1. So what that means is that we have made a transformation to a graph of 5 to the x. Remember, 5 to the x, y equals 5 to the x would go through 0, 1, and 1, 5, and negative 1, 1/5, and it would be an increasing function, not decreasing. So it must be that we have made a transformation that flipped that. And how is it flipped? It's flipped over the y-axis. So that means that we're looking for a function that has a transformation, and that transformation is to flip it over the y-axis. Now, in order to flip over the y-axis, we have to have a negative on the outside of the function. Right? So, for example, negative 5 to the x, not 5 to the negative x. That would give you flipping it over the, oh, I take that back. I'm saying that wrong. Which one would flip over the x-axis and which one will flip over the y-axis? So this one we have a negative on the outside. A negative on the outside affects the y values. So if you were to negate a positive y value, it would flip it down. So actually we would expect to have something that looked like this. So that's not what we want. We want something on the inside. When I say on the inside of an exponential function, I'm talking about inside the exponent. We want a negative. That would have the effect of changing every positive x to a negative. So for example, the 0.15 would move over to negative 1,5. The 0.01 would stay the same, and then the negative 1/5 would move over to 1/5, and it would look more like this, which is what we want. So we want a negative on the inside, so we want something with a 5 to the negative x. And we don't want a negative on the outside. Well, the only two options we have with a negative x are these two, C and D. And one of them has a negative on the outside as well, which would have flipped the graph downward, which we don't want. So we can eliminate C as a possibility. So the answer is going to be D. Okay, another thing you could do if you weren't following that argument is really just plot some points, right? There's nothing wrong with that. So x, f of x, if I plug in -1, for example, I would get 5 to the negative of -1, which is going to be 5 to the first, or 5. So -1 should go through 5, and look, it does. Okay, and 0 would be 5 to the -0. That's just 5 to the 0, or 1. So it should go through 0, 1, and it does. And then 1, 5 to the 1 would be 5. Sorry, 5 to the -1, excuse me, would be 5 to 1/5. So plugging in 1, we would down a tiny little number of 1/5. 1/5. There we go. All right, so either way, you can see that the function is going to turn out to be D. Remember, you can ask questions by typing into the comment box. All right, now we're going to look at a couple more questions from the review. I'm gonna go grab the review page here. Test review printouts. Okay. I want to point out to you that there are 2 questions here on the review which involve compound interest. Next to these 2 questions, I've posted 2 videos to explain the 2 different compound interest formulas. Those are compound interest like this one. Oops. Come on, pen. It won't let me. Okay, so this one is where you're told that you're earning 4% interest compounded, let's say, here we say semi-annually, which means 2 times a year for 5 years. And then here we have one where it's continuously compounded continuously. So in these 2 videos, it explains which variable is which quantity and how to calculate it. All right, so, oops. But now let's shift away from exponential functions, and we're going to look at a couple of other items from the review. That we have not worked in class, so I want to make sure you've seen them at least once. So let me copy this guy here. Okay, so the first thing on the review that you may not know how to work yet is find the domain of the function f of x equals the square root of 3x squared minus 11x plus 6. All right, so this combines 2 concepts which we have discussed in class. And these are the 2 concepts. One, when you have a function of the form f of x equals the square root of some expression, to find its domain, the domain of f, we need to determine for what values of x the expression under the radical, the radicand, is greater than or equal to 0. So you have to apply that idea here. But when we do that, we'll be solving a quadratic inequality. And we talked about how to solve a quadratic inequality in class, but we haven't applied it to this context. So let's go ahead and solve this quadratic inequality. All right, so to solve a quadratic inequality, we cannot just simply rearrange and get x by itself. So what we're going to do instead is we're going to analyze when is this expression positive or negative. We are going to think about, in other words, the function y equals 3x squared minus 11x plus 6. And in this case, where is it greater than or equal to 0? We can interpret that as meaning where is it positive. So we're looking for positive y values. Right? Greater than 0, it means positive values, or 0. It can be equal to 0. All right, so what we did in class is we went ahead and graphed the function y equals 3x squared minus 11x plus 6. But I said you don't have to actually draw the entire graph. What you can do is just set up a sign chart. Either way will work. If you're going to use the sign chart method, then what you do is you find the values where the function would be equal to 0, and that divides up your number line into different pieces, and then you just check each piece to see where you have positive values. So in this case, setting 3x squared minus 11x plus 6 equal to 0, we're going to solve for x. So we can do this by factoring if it works, or we can use the quadratic formula. I'm going to guess that most people would look at this, and because the leading coefficient is not a 1, the factoring is not quite as easy. So maybe they would use the quadratic formula. So let me show you how you would do that. So remember, the quadratic formula states that if you have anything of the form ax squared plus bx plus c equals 0, then x is equal to the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. All right, so we know our a is 3, our b is negative 11, and our c is 6, so we're going to just plug in. So that would be the opposite of negative 11. Negative 11 is positive 11 plus or minus the square root of negative 11 squared is positive 121 minus 4 times 3 times 6 all over 2 times 3. All right, so that's going to be 11 plus or minus, let's see, this is 2472. Let's pull up the calculator. Yeah, 72. So we're going to do 121 minus 72 equals 49. So we have 11 plus or minus the square root of 49 over 6, but the square root of 49 is 7. So we either have 11 plus 7, which is 18 over 6, or 11 minus 7, which is 4 over 6. And we should reduce, so that's going to be 9/3 or 9/3. That's going to be 3 or 2/3. Okay. All right, so we're going to put these are the values that would make this expression equal 0. So we're going to put those on our number line in correct numerical order. So that just means that the 2/3 should be on the left and the 3 should be on the right. And then we're going to check points in between 2/3 and 3 by plugging them into 2x squared minus 11x plus 6 to see if we get positives or negatives. Remember, we want to know where we have positive or 0. We have found where we have 0. Now in between, we're either going to have positives or negatives. So if we plug in something to the left of 2/3, this is called a test point. We plug it in, we're going to get 0 minus 0 plus 6. 6 is a positive number. To pick a number between 2/3 and 3, we could use 1. That seems like a fairly easy number to work with. If you plug in 1, you're going to have 3 times 1 minus 11 times 1 plus 6. that's going to be negative 8 plus 6, which is a negative number. So we're going to put negatives here. And then we're going to try plugging in a checkpoint for a test point. And if you do that, you have 3 times 4 minus 11 times 4. So 3 times 4 is 12. Minus 44 plus 6 is going to give you, oh, I think I made a mistake because this should not have turned out to be, let's see here. Oh, I forgot to square the 4. Whoops. Okay, so it should have been 3 times 16, which would be 48, minus 44 plus 6. That's going to be a positive. Okay. So, by the way, the reason I knew that should have turned out to be positive is because I also know that if I were to graph this function, this the zeros that we got would be the x-intercepts. This is a parabola that with a positive leading coefficient, so that means the parabola opens upward. So to superimpose on our number line what the graph would have looked like had we graphed it, it would look like this, which is up on the ends and down in the middle. So that's another way to know that it would be positive, negative, positive. Okay, so now we have a sign chart. We can literally read our answer. Remember, our answer has to do with anywhere, any x values where the function f, we want x values are on the bottom and the function values or y values are on the top. We want to know any x values that make us have a positive or 0 for our function f. So let's highlight where we see that on here. So positives occur here, 0 occurs here. Positives occur here, 0 occurs here. So the highlighted segments of the number line are where we have the values we need to give us greater than or equal to 0. So let's translate this into interval notation. So we have all the way to the left forever, so negative infinity. And then it ends at 2/3, and we are including 2/3 because we're including where it equals 0. And then we're going to union that with, starting at 3, 3 gives us a y value of 0, and then everything bigger than 3 out to infinity gives us a y value that's positive. So this would be the solution to the exercise. Negative infinity to 2/3 and 3 to infinity. And you can see that's the answer that's given on the test review. All right, and then another one I wanted to practice was this one. It's an application again of something that we've seen, but we haven't actually done one like this in class. So let's take a look. It says a ball is thrown vertically upward with an initial velocity of 128 feet per second. The distance in feet of the ball from the ground after t seconds is given by s equals 128t minus 16t squared. By the way, this 128 feet per second they mentioned, they are already showing us how that applies to the problem. They have created an equation using that. You'll see in calculus how to do this yourself. So for what interval of time is the ball more than 192 above the ground? All right, so if this is your distance s above the ground, we're wanting s to be greater than 192. All right, which means that 128t minus 16t squared has to be greater than 192. So this is a quadratic inequality, and I would like to use a sign chart like we did a minute ago to solve it. But in order to make that work, I can't have 192 on this side. I need a 0. So I'm going to subtract it over. I'm also going to write this in descending order of the exponents. So on the left already, we have negative 16t squared plus 128t. And then I'm going to subtract 192 over to get 0. So why do I do this? I do this because I want to make sure that I know what I'm looking for. What I'm looking for is greater than 0, or in other words, positive values. So how do we find that using a sign chart? Well, we find where it equals 0 and then divide up the sign chart into segments. So I'm going to set negative 16t squared plus 128t minus 192 equal to 0. Let's see if we can divide to make these numbers smaller. Let's start with 16. Does 128 divided by 16, that's a whole number. 192 divided by 16, also a whole number? Yes. So I'm going to divide both sides by 16, or actually negative 16. Divide everything by negative 16. Okay, so we're going to get t squared, and then 128 divided by 16 turned out to be 8, so 8t, and then 192 divided by 16, oh, that should have been a negative 8t because I'm dividing by a negative, so. And then dividing negative 192 by 16 gives us positive 12, and 0 divided by negative 16 is 0. All right, so now we can factor this guy, and let's see, I think we can actually use, factoring will be nice, because what two numbers multiply to give you 12 and add up to negative 8? That would be negative 2 and negative 6. So we can, since the coefficient is 1, we can just jump to the end, and this is going to be t minus 6, t minus 2 equals 0. Setting each part to 0, then we get t equals 6 or 2. So I'm going to come back up here and draw a number line. X values on the bottom, and the values of the expression or the function, I don't want to say that because we've changed the function. Negative 16t squared plus 128t minus 192. So we want to know where those values are positive. So I'm going to plot 2 and 6. That's what makes the expression equal 0. And then I'm going to check points in between, or use my knowledge of the graph of this guy. This would be a parabola that opens downward because a is negative. It's less than 0. Negative 16 is less than 0. So if I were to draw a graph of this guy, it would be facing in this direction, which means the y values would be negative, and then positive, and then negative. All right, if that doesn't work for you, then another thing you could do is just look for a point to the left of 2, like 0. Look for a point between 2 and 6, like 4. And look for a point bigger than 6, like 8. And plug those in, and you'll still find that you get negative, positive, negative. Okay, but what are we looking for? Well, go back to the original inequality here where we have greater than 0. We're looking for positives. So we're looking in between here. So our ball is going to be at least 192 feet above the ground from 2 to 6 seconds. And notice that that's the answer they gave, between 2 and 6 seconds. All right, so that's all that I was going to cover today, but if you have any questions, please feel free to type them into the chat line, and I'll be happy to help, or send me your Ask My Instructor questions. I do love to receive them, and I try my best to prioritize my response to you, so it's a good way to get in contact with me. Okay, so remember to work on your test review in my math lab as the time approaches. And I hope you guys have a good weekend. I'm going to get off the chat with you because I have another chat coming up at 11. But don't be a stranger. Remember, this is a blended class, and you are supposed to be contacting me outside of class time as needed. Okay, by the way, if this video was helpful to you, please give it a thumbs up. That helps other students to find the video.